Hi, Fabian. Shall we make a quick check if the audio works?
Sorry?
I just wanted to make a quick check if the audio works.
Well, it's perfectly fine.
Excellent.
I just had to find the tab first of all.
Okay, good.
What's the background?
That's Princeton in spring with a connecting the dots banner. Yeah, but I tried to make it a bit nice for David, who certainly put a lot of work into the conference, and then no one could see Princeton in spring, and that's apparently Princeton in spring. Yeah? Hi, David.
Hi, Andy. How are you?
Good.
That was
I just made a Princeton background for my Zoom meeting, so that you have a little Princeton of spring also from other participants and not just like you. So we have Jenny here.
Yes.
I finally fixed my echo. Your background looks nice.
Yeah, you had to.
Andy, I realized what I didn't put on the agenda was which talks were today. They're essentially the Monday talks, with I think 2 exceptions. First,
Yes.
Louise Skinneri is going today instead of tomorrow, and then somebody else moves from today to tomorrow instead. And that is
No. So Luis was on the second day, but is talking today, right?
yes, and then
Just joined on the right moment, Luis.
Yeah, I joined and I heard my name before I even managed to connect.
We're just discussing who's
the exceptions to the scheduling rule.
exceptions today.
And then the other one is Moritz. I don't know how you say his name.
Moritz Keen.
Yeah, is going tomorrow instead of today.
Exactly.
Otherwise, it's all the ones from everyone who spoke on Monday is going today, I think.
Can I ask, is the general idea to follow the same order as the order of the talks were given, or do you have another format in mind?
That's a pretty good question. Since we're doing this the first time today, this is gonna be a guinea pig session for this, and we haven't really entirely concluded what's the best mode for doing that. Whether we go step by step, one by one, or whether we do a summary and then have an open discussion. I think we should also consult with the people who are connected, and we'll all have to learn a little bit how this could play out. I think we wait a little bit, and then I will also make a quick call around if there is people, if there's someone with time constraints and would like to go, or really has to go first. Of course, we don't want to make this. I give my 1 minute and then sign off session. But of course, we understand that in this format, there's a lot of constraints for many people. So we can certainly try to accommodate this today in this session. We have 17 participants right now, which is already more than speakers. That's very good. It's a very good start. But, yeah. Hi. I made, for everyone who hasn't seen Princeton in springtime, apparently that's Princeton in springtime behind me. So I'll try to pay a little bit homage to our venue to be next year. I think we should start. David, do you wanna start? Kick that off, and then
Sure. I'm helping one person get the password for the meeting, so we at least have one person coming. Yeah, so we'll see how this goes. I think, as Andy was saying, the idea was, since we did all the talks last week outside of the main. Outside of time zones when most people can connect, we wanted to have a short discussion today, or however much discussion there was enthusiasm to have. So we're doing this today, tomorrow, and Thursday, always in this 4 to 6 o'clock European time, or 10 to noon East Coast time, US slot. So if you made it here, you know how to find it again tomorrow. The connection information should be the same. Good. So yeah, we asked all the speakers to make one slide, and we'll have them present it. I think what we decided to do for this experiment was to try to go through all the talks at the beginning, and then we'll sort of have a round robin of questions. I think what we'll do is, Andy, will you share the slides, or do you want me to?
Yes, I have them all prepared here.
Awesome. Okay, so we'll share them here, so we don't have to go back and forth. And I guess it means the order is determined by whoever slide you pull up next.
As a special service for this for the presenters, if they want to know, they can indicate to me before or after their 1 minute. Since we also want to learn how this works in such a virtual setting, I went through the statistics of download material in Indico for your contribution, and I went to YouTube and counted the number of views and downloads or views of your recording. If you're interested in the number, I can tell this, and if you want me to say it, I can do it. If you don't want to see that, to have that, I'm fine with it as well. This is really also for us to understand, did the format work in that sense, or and there are some very good insights. I think we will, at least from my side, I'm scheduled already to give with Fabian a summary of how this worked in Atlas, and I guess we will try to digest this a little bit in aftermath, and then also have it probably linked to this agenda. I think this is interesting since it's all a new situation for us. So bear with us if this works a little bit, let's say, not entirely round this afternoon. It's really the first session of this Q&A session, and we're gonna try to make the best out of it, and still encourage a discussion within our community, which was, to my mind, always the strongest point of connecting the dots. All right. Shall we go through the talks? I could offer that we go through in the order as it was on the agenda, which is probably the most, let's say, streamlined one for people who didn't know what would happen today, which then would be Cenk with with the summary of a quantum graph network approach to particle track reconstruction. Is that okay, Cenk? Are you ready?
Yes, I'm ready.
Okay, then let me try to share the slides, and now I need to see. Everyone called it CTD summary.
It should say Tusus.
It should say Tusus. Yes, here we go. That's it. Thank you. So, and now I try to share, and we should be good. This is share my screen. Review. Which one is that? Unfortunately, that I do not have the permission to share, and I would have to restart Zoom. Sorry for this inconvenience. David, can you share? Would that be okay?
Yeah, give me a second to catch up.
Yeah, apologies. I have switched computer and I have not given permission to share screen to Zoom. Excellent.
So should I start?
Yes, go ahead.
Hello, everyone. In this work, we try to build a quantum circuit model to do particle track reconstruction. We added on top of the HepTrackX project, which built a graph neural network, and we converted the building blocks of this graph neural network to quantum circuits. Here you see a very basic quantum circuit model that takes 2 nodes for classifying an edge, and applies a 3-tensor network, then tries to extract the edge information. And then we do machine learning. We train the circuit basically to learn the edge features. we presented the very first results at CHEP, and you can see the proceeding here. On the right, we have the training results for a single epoch. You see that we can get to AUC values of 0.8, and which is not really good, but for such a simple model, we think that it is pretty promising. But there are some issues when training quantum models, and that is they took quite a long time to train these models, but you can do really good things. In this model, we only had 41 trainable parameters, and we reached to AUC values of 80%. So it's it looks pretty good in that sense, but there is not an advantage that we showed to that would benefit us using the quantum model at the moment. But we are still trying to improve this model and trying more complex things with this. So this is it, I guess.
Very nice. You were. Do you want to know? Do you want to know the how many views you had on YouTube?
Yeah, sure.
That was. You were actually a popular person on YouTube with 18 YouTube views.
Nice.
And 5 MP4 views on Indico. So in total, you have 25 offline views of your talk past your recording.
Yeah, thank you.
Good. Then following the Indico order, we would switch to Florian, who summarizes his work on fast parallel primary vertex reconstruction for the LHCb upgrade.
Yes.
Florian Rice for that.
I went to the wrong one then.
Yeah. Can you hear me?
Yes.
Okay, perfect. Thanks. Okay, yeah, just to quickly recap. So yeah, we presented a new approach for primary vertex reconstruction for the high-level trigger for LCB round 3. The new approach is based on histogramming along the beam axis, where we take into account the uncertainties using Gaussian densities, as you can see here, a histogram in the left plot. And we implemented this algorithm on CPU and GPU architectures, just deviating slightly in the exact implementation with respect to how we assign the tracks when fitting the vertices. And in both cases, we took advantage of various places where you can make the algorithm faster by parallelizing it. And then in the end, it meets the throughput and physics performance requirements in both cases, and was chosen to be the nominal approach now for round 3. And that's it. Thanks.
Very nice. Thank you. And we would move to Gian Antonio with Track Finder. Oh no, you have a different. Do you have a different summary?
Oh yeah, I just modified slightly the summary.
Yes. Sorry, you have a different name. That's fine. Okay, perfect. Well, you're already up and going. I was confused by the title. But that's
I probably have the wrong one up then. If there's
no, this is Mutui's online track finder.
Okay.
That's correct. That's
if it just changed, this is the old version. But...
I just shrinked that to fit in the slide.
Oh, okay.
Can I just point out, Gian Antonio, that you did indeed win the style contest in being the best dressed speaker of a virtual conference.
Oh, really?
In all recordings. I invite everyone to go back and have a look.
Thank you. I appreciate it. All right. So if I can start. So hi, my name is Gian Antonio Pezzulo, and I've been reporting about the MITUI track finder algorithm that we use for our online trigger system. And the MITUI is a small experimental framework that is looking for a charge reacton favorable reading signal, which is an electron at about 105 MeV. And essentially, our detector system is very sort of basic. So we have a tracking chamber made with straw tubes and then a crystal calorimeter. And you can see the picture on the top right. And our trigger system is based essentially on online tracking. And we use two different pattern recognition algorithms. One uses the calorimeter information for seeding the search into the chamber of the pattern of hits, consistent with the track coming from the stopping target, where we shoot the muons, and then we look for this conversion electron. While instead, the other one is a more general hit expander algorithm that uses no assumption on the particle origin and just uses information within the tracker per se. So the good thing is that pattern recognition both algorithms provide to us a momentum resolution at the level of 3-4%. But then when we do the more precise chi-square fit, after the pattern recognition, we achieve a momentum resolution as it is shown on the plot on the bottom right at the level 1.4%. So something about the performance of the TDAC system is that we achieve a good rejection of a level of 2000 with the trigger efficiency, which is slightly above 98%. And we started also doing timing tests with a prototype of the TDAC system at the FameLab FCC Center. And we achieved 6.5 milliseconds per event in our performance of the online event builder. Thanks.
Thank you, Gian Antonio. Can I make a quick, a very quick feedback for people? Just try to have some questions. If you have some questions, note them down. I think I'll ask again in like 2-3 talks. If you already think it's too much different information, then we could potentially make a stop and insert some questions there as a first block. As I said, we are learning this as we're doing it, since this is the very first question. For now, I think we should go on to the muon tracking algorithm for level 1 trigger in CMS barrel summary, and the speaker is Jamie Leon Holgado, and gives a one slide summary of his topic.
Okay, can you hear me?
Absolutely.
Okay, so I'll start. So what I presented last week was the analytical method. That is an algorithm that is used for trigger primitive generation for the CMS level 1 trigger system that we will use during high luminosity LHC. So this algorithm uses the information from the DT and RPC systems in the muon chambers, and is already implemented both in software and firmware. So here in these 4 plots, what I show is the performance of this algorithm. So on the top, we can see the performance with respect to phase 2 simulation. So on the left, we have an efficiency plot, and on the right, some resolution plot. And on the bottom, we have performance with respect to real data. So on the left, we've got the injecting hits from the run 1, so it's real collision data. And on the right is from a cosmic sample that has been collected directly on the CMS detector using the prototypes that we have already installed. So the key point of the algorithm is that we have already tested it, we are using it, and we obtain much better performance than the algorithm that is used nowadays. And thank you, that's all.
Thank you. And next would be Jenny, Regina, talking about the track reconstruction on free streaming data from Banda.
Yes, hello, can you hear me?
Absolutely, well.
Perfect. So, yes, as you said, I presented my work on the quality assurance for track reconstruction of free streaming data at Panda. And the tracking algorithm I'm using currently for the free streaming data is a 4-dimensional cellular automaton procedure. And the reason why we use a 4-dimensional one, you can see at the bottom left figure that when we have event mixing, it will be really messy to use just a 3-dimensional algorithm. And what is a bit special about the way we do the track reconstruction of free streaming data at Panda, you can see at the top right figure that at the digitization stage, here the digits and therefore hits are sorted in time, and we will have pile up between events. And so the digits are not sorted event by event anymore. And what is new with this with this work is that now we have a task for actually evaluating the quality of the tracking. And the first results from this you can see in the bottom right figure. And the efficiency is quite high and stable for interaction rates between 0.5 and 4 megahertz. Thank you. That's my short summary.
Thank you. So next on the list would be Laurent Bassarat with the optical processing unit, which has been shown for tracking and calorimetry. And we had, for all of those talks, we already had a bit of discussion in the recording sessions. And I think I remember there was quite some interest also after Laurent's talk.
Okay, can you hear me?
Yes.
Great. Yes, so just as a reminder, the general idea of optical processing unit is that, well, most of the time we have nonlinear problems, and in machine learning you have some stuff like the canal trick that can solve them and linearly separate them. It can be approximated by random basis, and the optical processing unit, you can see on the left, is a way to compute just putting a signal of bits through, let's say, a white sheet of paper to get those random features that are already linearly separated, and it does the process fast. And so that's a physical device that you can access through a dedicated interface, and we used it to try if we could do something for HEP related problems. So first, for tracking, we used the two-dimensional dataset from the REM challenge. First, we tried to estimate parameters for a single track, had some nice results, went for a more complicated sample having the whole tracks. Again, it gave some results, but really far from even simple comparisons. And the second phase, we went to calorimetry, which is more remote from what we do here in this conference. But yeah, we had some complicated problems solved with CNNs on calorimeters, and we tried to project them on the OPU and get some results. Here, the results were more interested because we showed that the OPU is something to get good estimator extremely fast and with a few samples as compared to usual CNN where you have hundreds of thousands of samples and it takes a long training and optimization. So yeah, that's pretty much it. Thanks.
Thank you, Laurent. I think what we could do now is take this first block. At least that's my opinion, as otherwise we'd have a lot of different topics, and people will probably not stick to have the question sticking in their head anymore. And we could discuss this this first set of I think 6 talks. Would that be okay?
First out. Yeah, it's fine for me.
Okay, let's. We have 36 participants, so I guess it would be okay if you speak up. Otherwise, there is the raise hand feature, which you can use on, if you don't know where on Zoom, there's on the right side in the participants panel, you can raise your hand and then this should be shown. But we could try to just let people ask questions and speak up. So shall we go back in order and see if there are points and discussions and questions for the first contribution from, I don't want to mispronounce your name again, Tusuts?
Yeah, Tusus.
Tusus.
Yes, Cenk Tusus.
Okay. Does anyone have something to ask for Cenk? I do have a question though. if this is if no one else speaks up here. So you have used the TrackML data set.
Yes.
And I did not remember. Probably you said it. What was the score you achieved in your example, and how did that compare with the HepTrackX score?
So actually, I didn't check the TrackML score because the results are not really good. And here I only have 100 events. So it is not really comparable. And the performance is quite poor compared to HepTrackX. So if you look at the like AUC or the model scores for the HepTrackX project, it is very close to ideal. It's like the score is around 1.0. But so now we only have like the best score we have is 0.80. So I didn't compare the TrackML scores.
And as a conclusion, which you show at the bottom, there is like no quantum advantage is shown. Is that basically saying that's a cut off dead end street, and as to it's not the right tool for the problem, or is this at current what can be achieved, and what's the current understanding is? How do you see this?
So with this approach, I don't think that it is easy to get like advantage by using quantum computing, but maybe we can gain in some points. But even if we do, we would need quantum computers with distributable quantum computing systems, like we have in GPUs.
Right.
But, so it is really hard to build physically, and but this was more of an exploratory look. It was to just see if we can do this by using this gate type quantum computers. There are also works that does this with quantum annealing, but with this way, it doesn't look very promising.
I see. Final question, and a purely technical question, because all I did personally get into so far was running a 5-line hello world in some quantum Python layer emulator from IBM. How strongly is there a technology lock-in? Is this going to be the same GPU story again, just with quantum computing, that you have a vendor A and you write stuff only in render A, and then even if you have another gate type quantum computer of another vendor, is the transportability of the code to write, is this somewhere abstract, or are we hopping from one technical lock-in into the next?
So for this, we really need a high number of qubits in a quantum computer to make this faster. So with this graph neural network model, you see here a 6-qubit circuit. If we have a 6 by some number n qubits, we can parallelize this pretty easily. So if we run this in a 12-qubit computer, it would gain us double the time.
Okay.
But when you build these things up, and in the end, you also need to calculate the gradients for these circuits, and that also needs running the same circuits multiple times. So taking the gradients also adding another complexity to training quantum neural network models.
I see. Okay, are there other questions to this or comments to this contribution?
Yes, this is Shovik from Purdue. I have a question, Cenk. So this looks like a VQE sort of parameterized model, and I think you mentioned at the end that you do need a classical gradient descent optimizer. Is that correct?
Yes, the gradient descent is classical.
Okay, so I never really understood what the advantage then is. I mean, isn't there most of the time, and you know, what is the advantage? Because the optimizer is classical anyway.
So this was to test a quantum neural network model in particle track reconstruction. We looked if we can gain something, but it doesn't look very promising by just using this model. So what's the only advantage we have is we use less parameters compared to a complex graph neural network model, but nothing else.
I see. Okay, and so do you just use some sort of stochastic gradient descent to to get all these parameter values that you have?
We use the Adam optimizer.
Oh, okay. Interesting. Okay, thank you. Sorry, is this running on a simulation or you actually have 6 qubits on where was this done?
Simulation.
Sorry, this was simulation?
Yes, like complete simulation. And this circuit you see here is the most simplest form. The results on the right you see has 2 different circuits. The quantum edge network for the current run we have is 8 qubits. And for the quantum node network, it is 12 qubits.
I see. So but you do you have any results on real qubits?
No. If I want to run this in a real machine or maybe IBM quantum service, it would take so long time since they don't give that much run times.
Oh, okay. Thank you.
Interesting, very nice. Then let's move on to the second contribution from Florian on the fast parallel vertexing for the LHCb upgrade. Again, if you just want to jump in or raise your hand, I now saw Suvik had raised his hand for the one question before. Yeah, I missed that. Apologies.
No problem.
I think it's because I just gave you permission to see that, so that's my fault. I had a question actually, which is on the plot on the left. The peak finding, one of the steps in your algorithm is to do peak finding in this diagram, essentially, I guess. How did that technically get done?
So yeah, the peak finding, first it identifies what is called a proto cluster, which basically just consecutive bins which are larger than 0, and then it divides those clusters according to significant dips between the maxima.
Okay, do you have to worry much about close together clusters?
Yeah, at some point, of course, if depending on how you define the dip, and if the clusters are too close together, they will be merged into one, and you will not be able to separate them anymore.
But that would be mostly soft vertices that have a rather broad set zero distribution, right?
Yes.
That merge into, and I think you probably even see some candidates around -40 here, which looks like potentially two candidates that are not really separable from the C0 resolution.
Yeah.
I have one. If no one else wants to jump in, I have one question regarding the CPU and GPU implementation. How much overlap did you manage to do with these implementations? Is this you're maintaining 2 separate codes there, or you basically have similar algorithmic code and just wrapped into a different caller structure?
So at the moment, it's 2 separate codes, which at the moment are maintained separately. Yes. So there's not really an overlap right now.
I think that's a general issue we may have to solve the more accelerators come into game, right? Because you certainly do not want to have a too big divergence between code and performance then depending where you run on CPU, GPU, unless you have a full control over your hardware.
Yeah, I mean, yeah, of course, this is a general issue with, yeah. Yeah, because this is of course also true for other parts in the HLG or in the high-level clicker sequence between the CPU and GPU implementations, because there's not a lot of sharing or overlap right now.
Right, thank you, Florian. Are there other questions, comments to Florian?
Yes, this is Shovik again from Purdue.
Yeah,
Sorry.
now I see your hands raised. That's why I asked.
It's okay. No, a question about the peak finding again. How do you know how many primary vertices you're going to fit for?
Yeah, it's basically the number of peaks we find. This is the initial number of seeds.
I see. So this is some sort of an algorithm that scans through this histogram and tries to find the number of peaks as well. Okay.
Yes, exactly.
Okay.
So yeah, so what you get from this algorithm is the positions of the peaks and of course the number of peaks.
Oh yeah. So then my question was, have you cross-checked back with the true number of peaks, the true number of vertices that you put in, and see how many times you get it right, and how many times the tracks actually get the right associations?
I don't think we have checked that explicitly, but yeah, that's something we should double check in the future.
Right. So so then what do you mean by efficiency on the y-axis then, if you don't know this is the truth efficiency?
Okay. I mean, sorry, I thought you were just talking about the peak finding step, but the peak finding is also then followed by the vertex fit, of course, and the efficiency is then really the number of fitted PVs divided by the number of simulated PVs.
I jump in here for one clarification question. Are you matching those? Because we find this more and more problematic the more primary vertices you have, that you actually come up with a very clear matching criteria. It's already difficult in some sense to say when is a track found, and it gets more complicated when is a vertex found. Are you somehow having a weighted number of truly associated tracks, or?
So for the moment, because at the moment we don't have too many PVs on average, like 5 or 6 per event on average, we can still get away with matching just by distance. So we consider a simulated PV match to a reconstructed one if it is within a certain distance in SAT, taking also into account the uncertainty on the reconstructed PV.
I see.
Okay. So you have done the matching, but that's not part of this efficiency on the y-axis. That is just a division. That's just a simple number by
no,
number.
sorry. Yeah, to be clear, yes. So we've done the matching, and this efficiency is matched.
Matched efficiency.
Yes.
Okay.
Right. Let me have a look for other raised hands. There's no more raised hands for Florian's talk. Then I think we go further to Gian Antonio for track finder in MuQE trigger, so online. My notes. Does anyone have a question for or comment on Gian Antonio's presentation? Let me ask one. The timing test of 6.5 millisecond, is that sufficient for your triggering window, or is there still work to do?
For it's not enough. Yeah, we have a requirement of 5 milliseconds. And I mean, we already had strategies that actually can bring this down to half of that. So at about like 3 point something milliseconds, but that would also affect the efficiency at the level of about bringing it down to about 90%. But we are trying to do a lot of improvements in our modules, software modules, using the trigger sequences to actually get it down without affecting the efficiency on the signal. So yeah, we're still working on that. And there is also there are also some side to bring actually on FPGA some of the early part of the reconstruction, referring to the heat preparation and the filtering, which it could be maybe implemented on FPGA, on the FPGA that we have on our DTC units. So yeah, it's a lot of R&D ongoing on that.
Thank you, Gian Antonio. Anyone else a question or comment on Gian Antonio's presentation? Then I think we should move on to Jenny, Jenny's contribution on the track reconstruction for Panda. Bring that back up. Thank you, David.
I think you skipped Jamie instead of Jenny.
I skipped Jamie. I'm sorry. Right. Yeah, my bad. That's muon tracking algorithm in L1 for HLLC. Are there any comments, questions for Jamie?
I had what's probably not a software question, but the aging effect is rather dramatic. You're expecting. How well understood is that? Is that sort of an extrapolation of a simulation, or is it something more reliable?
Yeah, there's a longevity group actually in the DT group that uses the installations in GIF++ at CERN. So they have irradiated a concrete chamber for quite a long time. So it's extrapolation, but it's also based on real data. So there have been a lot of studies about that.
And is there something algorithmically to do about that in terms of, I guess, a way of trading off efficiency and purity, I guess, or
can you
or
start
not so
the
much?
question again? I didn't hear you.
Oh, yeah. Is there a way to address that? So it's sort of getting addressed by adding the RPC information, but is there something in your AM algorithm that you can do about that in terms of trading off efficiency and purity, or is it just sort of the way it is for this algorithm?
This aging means that we don't get a hit in that cell. So if we don't get a hit in the cell, we cannot do anything with the DTs. So either we use the RPCs or we prevent this aging. That is something that we are trying to.
Okay. All right. Thank you. Yeah.
And that's the aging effect. I'm going to add a software question since David said there was no software. It's not a software question. I'm going to add one on top. The aging effects, are you actually implementing that in the simulation, or it just starts blinking out or blacking out channels to a rate that's expected from the test beam data?
No, so we have a simulation that has not aging. So it's we use the same phase 2 simulation for everything, single muon simulation, and then on top of that we say that the efficiency of this concrete station is some number.
Okay.
And then we eliminate the heat or not. Yeah, sorry.
It's not such that there is actually a digitization implemented that tries to digitize in an age detector.
No.
It's efficiency on top.
Yeah, it's efficiency. Yeah.
Okay. Well, apologies again, Jamie, that we jumped over you.
Don't worry.
Yeah.
Don't worry at all.
And we move now to Jenny then, if there's no other questions. So anyone? No one is raising their hand for Jenny's presentation. Does anyone have a question on this?
I guess I had one from the, it's not illustrated by any of the graphics, but the sort of timing information you added, sort of 250 nanosecond, if I remember.
Yes, exactly.
Level of agreement. Did you consider try correlating the sort of drift time you expected in the most likely cell location after doing track fits? As maybe as a final cleaning step, nothing else. In the sense that you know where in the cell the track.
Yes, exactly. So we are not using that information here actually, but we do have an algorithm ready for that, and we need to make this compatible with the actual quality assurance procedure. So when we can use that algorithm together with the quality assurance, then we can check how much it affects the efficiency if we include so this is the drift circle information. So yes, that is something to do in the future, but this has not been done yet. No, if that is what you meant using the
yes, exactly. Thank you.
Drift circle. Yes, so we can use it, but we need to make it compatible with the quality assurance. Yes.
Jenny, remind me, please. The software of Panda uses as an underlying processing framework root. Do I have that correctly in?
Yes, that's completely correct. So we use root, and we also base our program Panda root on FAIR root, which is common for most FAIR experiments.
Right.
Yes.
So this 4D cellular automaton implementation would be practically available on a root in a root event loop. It's based on root algebra classes, etc.
Exactly. You mean that one can use it event by event? Yes, exactly. And that is what is new now, that we have adapted this specific algorithm to work on the digits, or rather on the hits when they are time sorted instead. So we fetch the hits in chunks instead. But yes, classically it's being done event by event, and that I showed some results of also to compare to the no, sorry, that was for the 3-dimensional cellular automaton. But yes, so if you look at the plot here for the interaction rate, the results at the lowest at the lowest interaction rate, that corresponds to the efficiency we get if we run it event by event, basically.
Sorry, one more question.
Yeah.
Is your software stack open source?
No, you need to get permission to access it. So the FAIR root is open source, but not the
FAIR root I'm aware of. Yes.
Yes.
So FAIR root I'm aware of it. So, but Panda is just the Panda. I don't know how your software.
Panda root.
It's Panda root.
Yes.
The Panda root is on top of FAIR root.
Exactly. Yes.
For the Panda collaboration. Okay.
Yes, exactly.
Thank you.
Thank you.
Are there more questions on this? Otherwise, we move to Laurent, if I have it correctly in my... Yes, Laurent.
Yes.
My slide sharing will update eventually, but I made my computer unhappy, so maybe go ahead in parallel.
We had just a reminder. I think one of the questions was how big and how expensive is this unit for
the UPUs?
Yeah, the optical processing unit. We had this in the recording session.
Yeah. So as David had answered, the price of a unit is the order of 10,000 euros, and the size, well, it can go into a rack of in a computing center, whatever. It's really like it's a shoebox basically. It's 10 by 40 by 40 centimeters, something like this. But it really can go into a rack and be used in at a computing center.
Yeah, so very, very interesting. The first time I had seen this idea, I didn't even know that the concept of random matrices, how you use them. I think that is really a bit mind-blowing, that this actually helps you to sparsify the information. Yeah.
It really took me some time to really go to the bottom of the idea and understand how it worked. But yeah, it's a really a way those. Well, in my talk you have some link to the original article, but you have this idea of using multiplication by random matrices to extract some random variables that allow fast linear algorithm to work, and it's kind of mind-blowing. And the time bottleneck is those multiplications between CPUs or GPUs by random matrices. And well, just going through this white paint is is a really nice idea to have this idea random matrices physically. It's a nice concept. Yeah. But then the question remains, is it applicable to the problems we face? And that takes some bit of thinking.
Do we have a question for the optical processing unit? For Laurent. I think then we're through the first half of this discussion session, and we're gonna go. I think 6 talks was sort of okay for almost everyone now. I think to keep in mind. So I would suggest we do the second 6 and then go in the same manner through, and everyone can add questions, comments to the contributions. Then we would start with Louis Henry or Louis Henry. Louis Henry, French?
Louis Henry, French
okay.
Indeed.
The hybrid seeding at LHCb.
Okay.
The screen will jump over, I think, soon. It's a...
Sorry. I can only see about it. Okay. So let me just load it on my side very quickly. Okay, so yeah, the hybrid seeding is the standalone reconstruction algorithm of the forward tracker, which is called also SciFi of LHCb. So these are the 3 tracking stations after the magnet. And this hybrid seeding needs to run inside of the HLD2 trigger, which means it has to operate through some, some strict time constraints, and we need to reach a throughput of around kilohertz per node. And the principle of the hybrid seeding is an iterative search. So we define momentum windows And these momentum windows actually define also search windows for different hits. And then through these iterations, we clean up the environment, because if we were to tackle the whole search at once, it would be a bit complicated and too time consuming. For each iteration, we use different seed layers, hence the name seeding. And the choice of different layers actually covers for hit inefficiency. And the iteration goes firstly a track search in XZ, so a double search that goes to triplets. And then we search around the parabola that we can define with the triplets. And then we add some Y hits that allow us to reject ghosts and use this bin half cluster approach. And putting all that together, we reach the efficiency that I show at the bottom. So at high momenta, around 95% efficiency for non-election tracks, and for quite a small fake rate, so less than 10% fake rate for most LHCb events, and all of that for a share of the timing of the current HLT2 implementation that is smaller than 5%. Yeah.
Thank you. That was very clear. And then we move forward to Louise.
So there's actually two, Luis has two talks actually.
Ah, Luis has two talks.
Yes.
Yeah.
Just to make life complicated for, let me see. Let me move to the second one. Yeah, I couldn't list names twice this time, so. That is this time. I think it updated. Yeah,
it did. Okay, great. So this one was a bit of a longer talk about the whole status of the CPU implementation of the HL21 trigger in LHCb. HL21 is the part of the trigger that I've surrounded in red on the sketch at the right of this slide, which has to deal with a 30 megahertz frequency of non-inelastic collisions at the LHC. And it has to reduce the data rate for around 40 terabytes per second to 1 or 2 terabytes per second, which is quite difficult. And what I presented in our talk, more or less, was a review of all different algorithms and how they progressed through the last year. And one of the ways I showcase the progress is, in fact, the sketch at the bottom left of this slide, where taking one technology in particular, so some AMD processors, we have gone from 800 nodes to fewer than 200 for running the whole HLT1 sequence, which means that if we want to translate that, we are able to actually read our data, partially reconstruct our events, and trigger at a rate of 30 megahertz for around £1 million Swiss francs. And this has been made possible by changing the design of our algorithms, but also use our architecture in a more efficient manner. And for example, the velo, I pointed out mostly the evolution of the velo tracking, which is still half of the timing of the HLT1. And it has gone much better thanks to the use of the SIMD instructions. And I wanted to point out as well that there was another talk for the GPU approach. And right now LHCb is choosing between these two technologies that actually allow to run the trigger with the timing and budget constraints that I've underlined. Thank you.
Thank you. So you have two, not a third one, right?
Yeah, that's about it. So see you in 10 minutes.
Then, Louise, your turn.
Hi, sorry.
Hi.
All right. So this was a presentation about level 1 track finding at CMS for the high luminosity LHC. So for CMS, the inclusion of level 1 tracking is really critical in order to achieve the required event rate reductions. And what CMS uses is a concept that is based on these so-called double-sided PT modules that is shown on the top right here, which performs hit correlations already in the front-end readout electronics. So the CMS system is an all FPGA-based system, which intends to provide full detector track reconstruction at 40 megahertz within a 4 microsecond latency. And so in order to tackle the associated large combinatorial challenge, we use very extensive parallel processing, both in space and time. And the algorithm that we are using now is a so-called hybrid algorithm, which combines a classic road search tracklet algorithm with a Kalman filter fitting. We're also extensively exploring what we refer to as an extended tracking setup, which intends to identify displaced trajectories from long-lived particles. And we're now working towards the specifications of the final system and the next level hardware demonstrators. And I showed here on the bottom just an example of the formation of a tracklet, which is propagated and then fitted with a Kalman filter, and 2 example figures of the tracking performance, either the Z resolution that we get, which is very important for the vertexing, and the improved tracking efficiency for high D0 particle with this extended tracking.
Thank you. I would say we had 3 talks now. Shall we take, because otherwise if we run through, we have quite a big list. Probably take a 4th and then make another round of question, and then we have 3 to go. I would suggest that if that is fine with people. Then we would move to Marian.
Yes,
you'll even have 4 to go, so that's perfect.
Ah, yeah, right.
Sorry, Marian.
Okay. So I've presented an update to a hybrid deep learning approach to vertex finding. It is hybrid because we start from tracking and then do a kernel generation, and only then in the cluster searching have a convolutional neural networks with a customized cost function. In the future, we also plan to replace this kernel generation by a machine learning algorithm so that we have a sort of end-to-end vertex finding algorithm. We have shown that the performance was improved if we apply this vertex finding algorithm to PV finding in an LHCb-like environment. And the improved performance is driven by the architecture choice of convolutional neural networks. The next, or the last thing I want to highlight is that we have privately deployed the vertex finding algorithm as a PV finding algorithm in the CPU version of LHCb's high-level trigger. And on the plot on the lower right, you can see that we now get more pronounced kernels when we use the measured track covariance matrices. The next step there is to train with this LHCb, the full LHCb simulation, and also benchmark it with common LHCb tools. And if you want to play around with this code, you can go to the open source standalone package. Thanks.
Thank you. Then I'd say we make a stop here and go through these 4 talks with questions and comments. So if you jump back to the first one. The seeding talk, the first talk of Louis on the seeding. You can again raise your hand if you have a question, or as there is not an overwhelming people fighting for the microphone. You can also, I think, just jump in. Are there questions for Louis on his first talk on the seeding?
I had one. You talked about a requirement of five out of 6 hits. Is that something you have to worry about in context of robustness against detector problems?
You have to worry about hit inefficiency. Firstly, you have the technology itself where you can have a hit that is missed even if it should have fired the layer. But also you can miss a layer because you went actually between 2 maps, for example. there are some small holes in the center that are millimeter wide. And it's quite improbable that a given track actually passes through 2 holes in a row, but it can pass through one, especially considering that these holes, there are some that are quite close to the center of the XY plane where the beam hole is and where the largest multiplicity is.
Sorry, could you repeat a seed? A seed is a triplet, right? In your definition.
Well, there are several, well, the thing is that it's also called hybrid seeding because it produces tracks that are used as seeds for other algorithms, but also, yes, a given iteration starts with 2 layers, 2 X layers. And so you take everything from a seed of a doublet of X hits. And then from this doublet, you can guess with pretty good accuracy where the third one should be. And from these 3, you get the parabola that gives you an equation. Well, you get an equation that gives you where all the rest of the hits should be.
And for your efficiency plot, you show at the bottom to the left.
Yeah.
This, what's your denominator there? Are you counting all particles, or are you counting particles that are findable? Meaning
findable. Yeah.
They're findable, so they need to at least have left 3 hits in the detector for basically.
Yes, they need to have left a hit at least in each station of the sci-fi. So right. 3 hits minimum, yeah.
Okay. So technical efficiency in some sense.
Yes, it's basically this 5%-ish that you're losing, a bit less than 5%, is related to your acceptance windows for example, the third hit search especially.
Which is why it falls then at low momenta, because you start mismatching your search windows more often.
The thing is that most of the combinatorics are dealt with in the XZ search. And you need to put some pretty strict hypothesis about where your hits are. And the third hit is where you lose some efficiency, but if you were to put anything wider, you would the timing would blow up.
Right. Okay. Now, Maurice asked if you guys would be up for a virtual conference photo of this Q&A session, would mean everyone would have to switch on the camera for a second, and we make a screenshot. I don't know if this actually works, but we could give it a try.
Should we do that after going through the rest of the questions, and then people have a few minutes.
Let's do this. Yeah, that's a
good
idea. Yeah. Let's do this. Then, shall we go to your second contribution?
Mm-hmm.
Slide should come up soon.
Yeah, see it.
Does anyone have a question on this one, or a comment to make? I have a very practical comment, since I haven't not really done a lot with GPUs. Are you actually? How does this work? Are you following each time a new release of a GPU model comes out, and you need to basically buy a prototype and then test whether this is a better value for buck setup, or how do you approach this?
That's the competition. I think, right. This one was about the CPU side.
Yeah. That's a competition, right? True.
Multiple choices, right? I shouldn't answer.
Okay,
I guess
can you hear me now?
Yeah.
Okay, cool. It bugged out for me.
Sorry.
There was a question. If I understand the question, it was about how we tracked the progresses in GPUs, right?
Yes.
So then, well, the thing is that this topic was the CPU implementation. There is a later talk, I think, during this question session about the GPU implementation. So person would probably be better.
Yeah, right. I missed those up.
No problem.
Yeah, I can
For the CPU, the very quick point, there is actually a document, public document, that compares a bit the scaling as a function of the CPU model that was published this year. And so this is why, in fact, was chosen the EPYC 7502 for this graph. It's because it's one of the good compromises, let's say.
I see. Thanks.
I was curious, your talk, the SIMD implementations, it sounds like there's quite a fair bit of sort of generally usable libraries that you've implemented to support different SIMD. How broad of an architecture set does that support? Is that sort of well representative of covering well what's on the grid, for example?
So concerning the CMD implementation for the video tracking, there was a paper that was written. I think I referenced it in the talk, and the LHP team that was responsible for that developed some wrappers because not all architectures were covered. Yeah, I don't know if it does answer your question there.
Yeah, it does. Thank you. I think I missed the reference. I'll go back and find it.
Okay.
It's not to say that it's probably there. I just didn't see it.
I'm just checking quickly because or else it would be a bit annoying for you to find it. Let me. Yes, it is. So it's a reference for slide 12 on the plots. The plots are from the paper.
Cool. Thank you. I'll go back and look.
Okay. No problem.
Okay. All right. Then, Luis.
Yep, I'm here.
There's two raised hands. I hope I haven't missed those for talks before. There's Philip.
Hello. Hi.
Hi.
This is Philip from San Diego, and I was curious regarding the extended tracking and what was the main differences between the baseline and the extended tracking.
Right. So for the baseline tracking, what we do is that we form in the track seeding step, we form these so-called tracklets, which is a pair of stubs into adjacent layers or disks combined with a third point, which is the constraint to the beam spot. And so that forces the tracks essentially to be prompt. And so in order to relax that constraint to the beam spot, we instead form seeds from triplets. So we use 3 adjacent layer or disk combinations. So for example, you might have, instead of forming a tracklet from the beam spot plus layer 5 and 6, we use layer 4 plus 5 plus 6. And then in addition, beyond the seeding, the extended tracking is also combined with a 5-parameter common filter fit, so that you fit also for the D0 parameter.
And when the extended tracking is being explore with the triplets, do the individual stubs still have the same criteria on the? I suppose they must, because you have to read it out of the ETF2.
Right, exactly. So that is one of the constraints, right? Because the way this stub formation work, the correlation of hit cluster at module level is that pass versus fail, where pass is basically consistent with a track above 2 GeV, that assumes that the track is coming from the primary vertex. And I didn't have plots of that in my slides, but in the link where there was some link to where the extended tracking is discussed in also more detail, you can see that basically the way the windows are, that if you look in the innermost layers where you're close to the beam spot, you can't go to very high displacement just because the way the windows are set up. But then as you get to the more outer layers of the detector, you can cover larger displacements.
Thank you.
Yeah, and maybe I should just also add that the reason for that is that in some sense, ideally, you would have all the hits, right? And you could just do whatever you want, but the stubs are there to reduce the data rate that we have to process and read out from the silicon detector, and so that's sort of what sets the constraints.
Thank you. Then Gian Antonio, I think you also had you raised your hand.
Yes. So yeah, first of all, thanks for the very nice presentation. I thought it was really, really comprehensive. It was really interesting. And mine was actually a curiosity, which is related to the previous question. So in the extended tracking, so when you actually you see the search with these triplets of tabs, do you start from the inner layers and you go outward, or you do the other way around from the outer layers and then you go and search for the other stubs in the inner ones? Because I was wondering that maybe for occupancy reasons, starting from the other side would be advantageous to converge on searching for a track, but maybe there are other reasons that I'm not thinking of. Thanks.
Yeah, no, that's a really good question. I mean, so actually, indeed, what we do is for example, for the combinations that we use for these triplets are they don't. I mean, this is all configurable, but currently what we're doing is we don't use the innermost layer in the seeding. But for example, for layer 4, 5, 6, it actually indeed starts from layer 5 plus layer 6, and then it tries to form a triplet by adding layer 4. And similarly we have another seeding combination, which is layer 2, 3, 4, but there it again starts actually from 3 plus 4 and then adds layer 2. But for example, if you have one of these seeds in the middle of the detector, in terms of finding other matches to form a full tracks, you still have to do the propagation both inward and outward. I don't know if that was quite what you asked, but
yeah, thank you.
Mm-hmm.
Great, thanks. If there are no other questions, comments, we move to the to Marian's discussion, and let me just see if someone raised a hand here. No raised hands. Marian, I would have a discussion just on a word that triggered me. When you said that you showed the performance as on an LHCb-like environment, was this just meant you had your own let's say toy simulation and showed it on that, and then later on you deployed it to LHCb and are confirming it? Did I understand that correctly?
That's exactly right. Exactly. So up to a few months ago, the code was completely standalone. So you can run it from the Pythia generation up to the PV finding as in a standalone package. It's working within Conda, and there's a proto tracking, and this is sort of simulating the LHCb environment. And actually, after we've deployed it, we've done some cross checks, and it looks like this this toy we have set up is quite good. So represents the LHCb environment quite well, even though it's simplistic.
Okay, and how does the integration? I mean, Conda is a quite different framework to run within than LHCb Gaudi. How did you solve that? Or is what you're showing still running within, let's say, post-reconstruction and just using LHCb data?
So we're actually using the production tracking that is currently in the high-level trigger software stack. So we're replacing this proto tracking and then taking directly the output from the production tracking, doing the kernel generation as we would do it in the standalone. So this is rewritten. This was in Python. This is now in C++. And then the convolutional neural networks are taken from PyTorch. And PyTorch is not part of the LHCb software environment yet, but we can do this. So this, so I'm taking PyTorch from the SFT software stack currently.
Are you trying to specify? Are you planning to call this directly from Gaudi?
Yes, it is already.
It is already. Okay. Thank you.
I guess I had a question. Your talk mentioned a bit about KDE needing sort of not being fast enough, which I think I understood well from the slide. I was curious, what sort of speed up factor do you need to get out of a machine learning approach that you're considering to make it sort of practical for LHCb?
We're talking about orders of magnitude, so 10 to the 4 factor speed up. This is because the current implementation is really calling Minui, and if you write a proper minimization there, you can easily gain these huge factors there. And if we manage to replace it by another machine learning algorithm, this will also be fast enough. And then if this would still be if this would still cost too much time, there are some pruning. There's now some pruning with the newest PyTorch release, which we want to look into, and there are other models where we can get rid of weights which are close to 0 in this CNN. So I think we can actually manage to get this huge speed up factor that we need.
Quite ambitious, 10 to the 4, but I'm happy you're confident to do that. Yeah. Are there more questions?
Of course, lots and lots of Minui initializations.
Yeah,
that's one easy way to slow your code down. Indeed,
absolutely.
Yeah.
Right. If there's no more comments, we're actually pretty well in time. We could follow Maurice's suggestion to try to make a virtual conference photo if people would be up for that. Then we would ask everyone to quickly, who wants, share the screen. If not, it's certainly not compulsory. It's quite nice. I actually can't even show all of those in one screen. I think there's a limit how many. Oh, what? One more? Excellent. Well,
some people are still turning on.
Some people are still turning on. Okay, let's have a look. I'll go back here. And one more, and then we. Paulo, very nice. Excellent. Well, new times, huh? To do this sort of conference photos. Very nice. Thank you. Shall we move back to the last 4 contributions, and then we go again through these 4, and then we'd have roughly half an hour left on the agenda to discuss this. I think that will fit quite nicely. David has shared already. I will stop my video, and
at least if I got the talk right,
yes,
am I in the right spot? Good. Okay.
We'll start with Philip on parallelizable track and pattern recognition HLLC.
Hi, this is Philip. And so our work's goal was to explore and build a parallelizable algorithm at the high luminosity LEC. And what we were focusing on was a CMS phase 2 auto tracker that uses the quote unquote the PT module concept, which is the same concept that mentioned from Lewis's talk. And this was designed to be able to suppress hits from low PT tracks by correlating the 2 hits from the 2 sandwich modules. And as you can imagine that the choice is driven largely by enabling the level 1 track trigger capability that Lewis is talking about today. So this correlated hits are what in our talk what we were calling the mini doublets, and this was the just quote unquote the stubs from the L1 track language, and these can be built in parallel, and that and so it sort of enabled us to think about applying a parallel algorithm even at the offline of construction stage. So then once the mini doublets are formed, then they can be built into what we call segments, and then link the segments and to build in multiple different kinds of track candidates. And this can all be done in parallel, as they only need to know their nearest neighbor to connect these dots, no pun intended. Benefits of the approach includes the potential speed up if deployed in a modern architecture, and it also does not rely on the inner tracker pixel seedings, which most existing algorithm relies on. And on another side benefit that includes the building the displaced tracks that comes for free, as it does not need to know further than the nearest neighbor, and our algorithm so far has not applied a tight beam spot constraint. And then also in the bottom plot demonstrates that a simple geometrical linking between these segments can work, by which you can see from the plot the true track appearing on top of the combinatorial background, which we then can cut out the combinatorial backgrounds on the side. And as a case study for the talk, we focused on the track candidate type that traversed the outer tracker barrel region without leaving no missing hits, although many different kinds of track candidates can be built. And on the number 6 of the box, we show the algorithmic efficiency for the building this kind of track candidates with no missing hits. And we show that very good efficiency can be achieved shortly above the 1 GeV threshold that we're targeting for muon gun events, pions, and electrons. Yeah, that's the summary of the talk.
Thank you, Philip. That was very nice, clearly structured. You walked us through, like even with bullet points through the talk. That's that's very nice. Let's go to the next next contribution, which is it Subic? Yeah, if that's correct on my list. David?
Yeah, it was hiding from me. I'm almost there.
Which is the second talk on using quantum technology. I have to say, these were the 2 most popular talks of today's session on YouTube. So there is probably some bias in search ongoing. When quantum appears in the title, you pop up earlier in the list.
Okay.
Subik, are you? Yeah, perfectly. We
Yes,
hear
can you-
we hear you fine.
Okay, so to summarize, the motivation for doing anything in quantum was to first, well, things are coming up, things are speeding up on the quantum world, and we wanted to find a HEPEX problem that can be solved today using a quantum computer, not in some theoretical way, or just really apply it. So the thing that we targeted was annealing, because that is practical compared to gate computing. So we were so the target problem we decided to address was primary vertexing, because that reduces to simply one-dimensional clustering of tracks to proton-proton collision points. So there you can see a picture of the D-Wave quantum processor at the end of a dilution refrigerator, and this is out there in Canada, so everything is done remotely. So the first thing we did was we formulated the primary vertexing problem for the D-Wave 2000 qubit system. Then we threw artificial primary vertices and tracks using published data distributions. Of course, we could not really deal with the real number of 23 primary vertices and thousands of tracks. So we have to start slow, and we started with 2 primary vertices, 10 tracks, all the way up to 5 primary vertices, 15 tracks, which is very low. But the D-Wave quantum processor does return the true clustering of tracks into the primary vertices with some degree of efficiency. And as you see on the plot on the right, this efficiency, so the black corresponds to the quantum, quantum efficiency, and the x-axis is the size of the problem expressed in the number of logical qubits. So that drops off really quickly for the black curve, but we also benchmarked it against simulated annealing. The only restraint there was that the simulated annealing has to finish in the same amount of time as the quantum annealing, because if you give simulated annealing infinite amount of time, then in principle you will always get 100% efficiency correct answer. So that's not okay either. So anyway, so we do see that the QPU performance is comparable to a modern CPU for some low numbers of primary vertices. The main problem is qubit instabilities. And so the outlook on this project is that we are now pursuing improvements in the quantum formulation itself and the execution. So with the execution itself, in the last couple of days, we found we get about 100 times bigger data sets can be done. And then we're also looking to a new formulation of the problem as well. This, coupled with the exponential increase in qubits and connectivity that we're seeing in the hardware, we think is going to encourage more realistic applications soon, especially in 2-dimensional, 3-dimensional, n-dimensional clustering as well. Thank you.
Thank you for this summary, Subik. And we go further with Thomas, right?
Yeah. Hi. So
your sound is a little bit difficult to hear, but I think we can manage.
Difficult, is this better?
Since it's not a 20 minutes, presentation, okay. We hope. I think you can just go through, and I think we'll manage. Yeah, go ahead.
Okay. Sounds good. So my talk was about the Allen project. This is our effort to create a working first-level software trigger on GPUs for LHCb. And in summary, this is the first implementation of a full software trigger stage on GPUs. Allen has been reviewed as a viable option for run 3 for LHCb. The final technology decision is in process right now. And also, Allen could allow LHCb to expand its own piece of its program. And so on the right here, I have a summary of the Allen architecture. You can see all the new partially created. And then on the bottom left, is our throughput performance. You can see that we can do the job of fully triggering on the full 30 megahertz data rate with 500 GeForce RTX 20 Ti, which is our reference card.
Excellent, thank you. Sorry for the sound quality, but I think it was understandable for this. And we'll go to one more 1 minute presentation, and then we'll leave the rest of the time for questions. And the last one is on Atlas minimum PT tracking from William.
Yes, can you hear me?
Very well.
Okay, great. So indeed, this is about the development of a low PT tracking framework for Atlas. So what we did is put together a framework that can be used in high pileup, because there previously existed a setup that can be run for events with, say, single proton-proton interactions, but ours can work up to, say, 70 or nominal run 2 pileup things. One of the key features of this is a region of interest. So we attempt to reconstruct tracks that are more or less close to the hard scatter. And I have a little diagram indicating sort of the space layout of the tracks on the top right there. This is meant to be applied to specific analyses, which we think will benefit the most from low PT tracking. For example, if you want to do a more thorough reconstruction of an underlying event, that sort of information can be useful. Not all analyses need low PT tracks. And so you can see on the bottom some performance related plots. So when you actually use low PT tracking, we can go down to about 200 MeV with relatively high efficiency and relatively low fake rate. However, for very low PT tracks, say below 200 MeV, the efficiency does tend to drop off and the fake rate tends to get high. But you can see in my slides or the larger presentation that we did some exploration as to how we might be able to improve that. And we think that reducing the fake rate is certainly something that can be done down here. So that's all I've got.
Thank you, Willem. Okay, and then I think we'll go back to the first presentation of this block and have Nick raised his hands on this one. So
yes, hello. Hi, can you hear me?
Yes.
Yeah, sorry, this is maybe a very naive question, but on the very bottom right plot, you can see clearly that you have this in your angular distribution. You have a very nice peak there. But you also have a sizable pedestal. What's the process for removing this pedestal?
Oh, so this is an n-1 plot, so we didn't remove it because we didn't cut on it. But if you can imagine cutting on it, and so most of the sides things will be removed.
Yes, but what about under the peak? Presumably that's got the same rate of wrong combinations too.
Right. The under the peak is a combinatorial background, and with the pileup 200, it's always an issue.
Okay, so this is just the intrinsic kind of fake rate, which is tolerable.
Right.
Okay, thanks.
I had one question, Philip, which was probably similar would fit similar to Louise's talk than to yours. It's more something which concerns your stub building, which is an input to your pattern recognition. Is the stub building, is that depending strongly on the aging of the detector? So if you start like breaking up these clusters because you lose channels, is this something you have to worry about, or since you're on the outer layers, this is not so much of an issue?
So the detector part of the health issues and everything, I may not be the expert to answer this question, but my understanding was that for the outer tracker, and then the people who are building this and are working on building the detector, my understanding is that for the outer tracker, it's better in terms of the radiation tolerance than the one in the middle one, because for the geometrical reason, basically.
Yeah.
Maybe Luis knows better on this. For me, I was focused on software development and for the algorithm development part, and And it's sort of I suppose it comes from the both sides, that the inner tracker will have their seedings as well, and then this will provide another seedings from the outer tracker. And so I think we're doing our best to try to provide as much as we can to the tracking, and not depend on one type of kind of detector's health. And I think this can, in that sense, I think this is a step forward to addressing that. Whether or not the outer tracker has a health problem going forward, and what will be the impact of it, I'm not 100% sure of the effect.
No worries. Okay.
I guess maybe I had a related question. Have you looked at how the sort of signal to noise in that bottom right plot, how that depends on the minimum PT you're trying to look for?
I have not parameterized it by the PT yet, and so I don't know the answer off the top of my head. But I suppose for more straighter tracks, they may get a bit more difficult, I guess, because then you lose a bit of a more handle on it. And yeah, so I'm sorry, I don't have a quick answer on that.
Okay, no, I was just curious because, of course, offline that the interesting tracking is at lower PT than this, let's say, or the time where all the time goes is at lower PT, let's say.
Right.
Okay. Any more questions to Philip? If not, let's move on to it was Civic, I think. Do we have any questions to Suvik on the annealing? I have one, Suvik. So you did run this directly on the D-Wave QPU, but I suppose you also ran it through the D-Wave simulation, right?
Yes.
How do they compare?
So the D-Wave simulation, as it stands today, is very poorly written, and it is a lot. It is so. I'm just trying to say it's a bad comparison to make, because if you actually look at the D-Wave simulation code itself, it runs as order of n square in the problem, where n is the number of qubits that you've used.
Yes.
So obviously it is much slower, and that's why I think D-Wave was saying, "Oh, we're so much better than simulation." So then I had to rewrite entirely from scratch the simulated annealing algorithm, the simulation of so I had to rewrite their code, and that is the comparison that I'm showing on the bottom right.
Okay.
And that is between the black and the red. And
so
the
this is your implementation of the simulation.
Yeah, which has also gone through their checking. So they also checked it and they agreed, yes, it's better. But I don't know if they actually fixed anything on their side. So.
Because being very naive here on my side, the development of such an algorithm for a QPU, you also sort of you can't develop and submit constantly to a hardware device, right? So you need some sort of a simulation during the development stage of your process, I would suspect.
Exactly.
Yeah.
So that is exactly true. I mean, in fact, we have been funded for the next year, but I plan to use most of the time, developing it on my software or our software framework first, and then we get a short amount of time to practice it, to really try it on the hardware. A few months maybe.
Suvik, this is Paolo. I want to point out D-Wave is not very keen usually to mention that, but they have developed a very good, in terms of scaling and performance, classical annealer, which is called NEAL, N-E-A-L. And we used it in a similar product. As you say, their simulation, the public one, is kind of embarrassing, but that one is not. It's actually pretty good.
All right, thank you. I will look into that then.
Is that accessible, Paolo? Yes.
Yeah, it is. It is. I mean, as I said, there for reasons we don't understand, it's not publicized, but it's open source. So, yeah.
Or if you want to show, if you want to show plots how you outperform simulation, then probably starting with with an embarrassing simulation is a good for your.
That was our uncharitable reading of why they did that. Because of course, if you use a good annealer, then your quantum doesn't look good in terms of performance.
Okay.
Yeah, so that was also my take home, because when I showed this to them in 2019, end of 2019, they said, yeah, go ahead with yours. And then I asked them to update theirs. They never updated theirs so far. So
okay. Interesting.
Let me see if I find the link in the next few minutes. I'll post it. Otherwise, we can do it.
No, I found it. I found it under the Neil, import Neil. Yes.
Yeah, it's pretty good. It's pretty good.
Mm-hmm.
Very good. So probably you can see how Neil compares to your written simulation. That's gonna be a benefit for your work. Very nice.
Thanks.
Are there more questions for Suvik? I don't see any raised hands. Okay, then let's move forward to Alan, and I can finally then ask my question, which I asked to the wrong speaker before. But first of all, I give the floor to anyone who's interested in raising their hand, having a question, or posting a comment here. Joe, I saw Joe has a. Joe, you're unmuted.
Yeah, sorry, I was muted. I just have a quick question. I'm curious to know if there's any plans to make the software for Alan open source, or if it is open source already.
I don't think there's anything stopping you from cloning it if you'd like to. So I mentioned how there's the possibility to turn Alan into a general framework, and you can't get Alan as a general framework, but you can get Alan with all of the LHCb algorithms in place.
Okay, thanks.
No problem.
Actually, yeah, that's very interesting. Whatever you did, Thomas, in the meantime to your audio, wonders, I can only say. You did
excellent
to your audio. If there's no other question, I addressed the wrong LHCb speaker, so I really had just a simple, rather stupid questions of your working mode, how often and what decision you follow, like new releases of GPUs, which are now becoming more frequently and from different vendors. Again, is this something you just have on the monitor? There's a new AMD release or whatsoever, and you try it out?
Yeah, I think that's basically the answer. Like every so often we see there's a new GPU, and we get the GPU and we add it to our plot, our performance plot.
Yes.
And I think it's the GPU vendors are fairly straightforward with, if you ask them, they can say like, you might expect this kind of speed up with this new model, so you can kind of get an idea of.
And with Alan, you have, if I remember correctly, with Alan you have the sort of decoupled the actual vendor language from the framework, right? So
not quite. So for example, like all of the algorithms are written in CUDA.
Yeah.
So this is NVIDIA specific. But so for everything CUDA can do, there's a one-to-one version of that in whatever other GPU, general purpose GPU language you want to use. So there's a lot of work going into compiling it for AMD and AMD cards, which is sort of an important point to be able to test on those. And I think that's possible now. or it's a merge request at this point.
Okay. Paolo, did you have a,
Yeah, it took me a while to find out to raise my hand because I forgot it was in the. So sorry, I didn't listen to your full presentation, but I was scrolling through the slides. So what is going to happen next with all these GPUs? How are you going to pick one essentially? I mean, is it just the best, the most throughput? So you're going to splurge for the V100, or is there some cost performance criteria that you're using?
Yeah, so I think there is a cost performance criteria. I think this will ultimately be some political decision that is made by the collaboration that I won't be involved in. But right now, so our card of choice is the RTX 2080 Ti. And we can do what we want to do with that. But as new GPUs come out, we expect that this will change, and this will be sort of a shopping procedure.
Interesting. Maurice.
Just a curiosity, it appears from your plot, of course, there aren't too many points yet, but as more points appear, that it's not linear, the throughput as a function of the teraflops. Do you have an insight into that? Is it just they're changing architectures, or what is it?
Yeah, so there are generational changes here, as well as just like incremental increases in teraflops. So like the 2080 Ti is the next generation from the 1080 Ti, and it's like they do things like increase cache speed. So it's like you see better than linear scaling between generations.
Very nice. Are there more comments or questions for Thomas?
I had one that may not only be for Thomas, but does LHCb have a public timescale for making a CPU GPU choice?
I don't know if that's public. Yeah, I think it'll be done soon, though. I don't know if Louis has any better idea about what the public position on that is.
I don't think there is.
Okay.
So we're not gonna put you on the spot here. Okay?
Sounds good.
I tried.
Thank you. You did try. Okay, and then let's go to the last contribution, which was William. Is there anyone wanted to get a bit more insight from William? Maurice?
I just wanted to raise a point for the participants here, not a question about that William would answer, but
yeah,
Patrick actually. The question is, it would be nice to have some kind of metric or methodology to assess what is the minimum PT that a particular tracking device should be able to reconstruct, some theoretical lower bound, or maybe not theoretical, maybe numerical lower bound to the PT based on occupancy. Because as we know, if you have a single track, you can easily figure out the PT that you can reconstruct for a single track in a device. But when you have pile up and occupancy, that will go up, because basically there's only meaningful reconstruction means that you have some sort of efficiency and fake rate that makes sense, and it's not you don't just reconstruct garbage. So that I've been thinking about what could be a good metric or figure of merit for that, but I don't know if anyone has already something in that direction.
There was an attempt for the FCC, I think, to establish this sort of analytically, by lining up hits in with their occupancy, and then check the compatibility of combinations between layers, giving the scattering limit. So combining basically the material contribution with the occupancy. It was rather difficult to grasp from my point of view to bring this in a meaningful metric. Yeah, I just remember there was the attempt. I think Vivek, no, not Vivek. Forgot who did it. That's the only let's say parameterized or analytical metric I'm aware of.
Well, I mean, I don't think it has to be analytical. You could do something like follow this prescription and you get the answer, something like that. And it doesn't have to be analytic, but it would be nice to have some sort of prescription.
Gian Antonio, you want to jump in here or have it?
Yeah, no, I just wanted to make a comment because that's a very interesting topic that was brought up. And one thing that actually is kind of really difficult also for large tracker chambers and such, and the comparison that doesn't usually take into account the fact that, for example, taking the case of low PT particles, right? So all the silicon-based devices, then with low PT, but also other tracking system, then multiple scattering becomes the largest source of the momentum resolution we get, right? So even if we reconstruct a 200 MeV track, the where do we set the limits where we say the momentum resolution is good enough that we can consider this reconstructed track to be good for doing physics? Because the fact that these are loopers usually in the tracking chamber, so there is a lot of multiple scattering that adds a lot. That's really the largest contribution in the momentum resolution. So it's really hard to compare chambers to chambers without taking the sort of the radiation length thickness, I think.
Yeah, so what we did, Gian Antonio, for the Atlas technical, what was it called, detector paper, the performance paper of the detector that was published prior to run one, is we came up with basically the critical or the momentum value where the intrinsic resolution equals the scattering contribution over eta. So you practically get some sort of an idea that when you're above your intrinsic dominated, when you're below your scattering dominated. That does, however, not tell you where the cutoff is, and that's what you were talking about right now. It's
a separate question. I mean, the question of resolution is fine, but just because you have a particular resolution doesn't mean you will find the track in any meaningful way. Like your fake rate will be higher than your efficiency, then of course it's not meaningful.
Yeah, interesting. I think that's really something we could think about in terms of classification, because as Maurice said, it's very difficult to understand what a tracker should potentially be able to do, and then which would ideally be the baseline to say that's what the algorithm should be achieving in some sense. The optimal algorithm, yeah.
Yes, exactly. Yeah.
Are there any more points to this presentation? Then I will just say I think we had to have managed quite an interesting, from my point of view, quite an interesting Q&A session, and we exploited the 2 hours. So I think that was also a rather good format for this. I may leave it to David to David if he wants to say a few last words or introduce the next 2 sessions. From my point of view, I pretty much enjoyed that, I have to say.
Yeah, I thought that went well. Thanks, yeah, thanks for everyone for participating. And yeah, we have 2 more tomorrow, starting tomorrow and Thursday. So please come back if it matches your schedule. Certainly these are busy times for everyone, but hopefully we'll have another good session tomorrow. So thanks again, everyone.
Very good.
Very good. And see you tomorrow. Bye.
Bye-bye.
Bye.
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 Bye.